Symmetry is one of the most important properties that we can identify for a matrix, both for theoretical reasons and because of what it tells us about numerical computations. So we're getting our first taste of it here, but it's actually a pervasive subject. Now, by definition, we say that a matrix S, if it's real, is symmetric if it equals its own transpose. So S transpose equals S, that's the definition of a symmetric matrix. Now, we haven't spent a lot of time talking about complex valued matrices yet. We'll have to get into that pretty soon. For a complex matrix, the right analog of symmetry is actually the Hermitian. So S star is what we call the Hermitian of a matrix. And that's the conjugate transpose. So not only do you take the transpose of the matrix, but then you take the complex conjugate of each entry. Remember, in the complex conjugate, you replace every I by a negative I. So the statements that we're going to make more or less go through when you talk about Hermitian matrices in the complex case. But for now, we're going to stick with real matrices. Now, another way of looking at symmetry is if you think about the elements of S, the symmetry condition means that Sji is equal to Sij. Or if you think about it in terms of just looking at the matrix, we have this main diagonal, and symmetry tells us that if you choose entries that are symmetric with respect to that diagonal, then they're the same number. So those red numbers would have to be the same, or I'm sorry, those green numbers would have to be the same, these two red numbers would have to be the same, and so on. So that's sort of a visual picture of what symmetry means. Symmetric matrices come up a lot in processes that are themselves symmetric. For example, if you think about gravity, the sun exerts a gravitational force on the Earth, and the Earth exerts the same gravitational force on the sun. It's a symmetric situation, and a lot of physical problems are like that. Another example where we have a symmetric matrix is in the normal equations. So remember, we have this matrix A transpose A that appears in the normal equations. I'm claiming here that this is symmetric. The way to show this is to just take the transpose of S. Remember that the transpose of the product is the product of transposes in the opposite order. And of course, the transpose of the transpose is the original matrix. So what I've just shown is that S transpose equals S, and that is what we need to check for symmetry. Okay, so the matrix that we get in the normal equations is an example of a symmetric matrix. And we're going to focus in on what that means computationally now. So if for a minute you imagine that we do Gaussian elimination, or LU factorization, without pivoting, okay, then we just get S is equal to L times U. Well, we can always write U as a diagonal matrix D times V. So the way we do this is we just pick off the diagonal elements from U, and that leaves us with 1s on the main diagonal, plus other stuff up here in the upper triangle. We don't know what those numbers are. I'm not saying anything about those numbers, but it's pretty clear that if you multiply out these two matrices together, right, in the diagonal you end up with something which is U11, right? Then we change the rest of the first row, but we don't care what that is. It's just something. In the second row we have 0 and then U22, followed by other stuff, and so on. So all I'm saying here is that whatever the original U matrix was that we got from LU factorization, we can further factor that U as a diagonal times a V, and V is a unit upper triangular. So remember, unit means that we've put 1s on the main diagonal here. Okay. So that's just another way of writing the original LU factorization. Where it gets interesting is that if we write S in this form of LdV, and S is symmetric, then it turns out that this matrix V is actually L transpose. And I won't go through the proof of this, but we'll just use this as a given fact now, that if S is symmetric, we can write it in the form LD, L transpose. L is unit, lower triangular, and D is diagonal. This is often called an LDL transpose factorization, or just LDL factorization for short. Now, remember I did say that we had to turn off pivoting for this to work. That's not always a good idea, as we know. There are a lot of matrices for which that causes numerical instability, or it even causes the algorithm to fail. In order to get around that particular limitation, we need one other property of the matrix that we get in normal equations, one that's a little bit more subtle than just symmetry.